So let's consider the general case of a dipole and how you compute the fields around a dipole. So let's consider that I've got a positive charge and a negative charge, and they are some distance d away from each other. And I want to know if I'm some point here, some y off of the midpoint. I know from before that the electric field there is going to be in that direction, but I want to know how big is the electric field. In other words, what's the magnitude of the electric field? And so let's see if we can figure this out. Okay, so if we're at some spot up there, okay, then we know that the electric field from the argument we had before, this is going to be some angle theta, this is going to be some angle theta. So that one and this one, we have two different electric fields here. We have the electric field due to the positive charge. We have the electric field due to the negative charge. Only the horizontal components add. So the total magnitude of the electric field is going to be 2 times EX. They both have the same EX. So that's going to be 2, we'll call it like E naught cosine theta, where E naught is just the field of one of them, okay? And so that's going to be 2 times K sub B Q over R squared. Okay, so that's R. So what is R? Okay, well, R is going to be square root of, well, in fact, we don't even have to do that. We can just Pythagorean theorem. R squared equals d over 2 squared plus y squared. Okay, and so we look at that. We say, okay, that's cool. Okay, cosine theta. Okay, so what's cosine theta going to be? Cosine theta is going to be equal to, if you look at this, cosine theta is going to be equal to d over 2 divided by r. Okay. Okay. So, kind of look at that a little bit more and say, okay, so we now plug all this stuff in. Okay, so now we're going to just plug all these things in here. Okay, and we are going to see, what does that do for us? Okay, and you look at it and say, okay, so that means that E, okay, is equal to 2 K sub B Q d over 2 divided by r cubed. Okay, so the 2's cancel. So that's going to be K sub B QD over r cubed. All right, and so that would give rise here to another thing here, because now we got K sub B QD. R squared was, remember, R squared was d over 2 squared plus y squared. So R cubed is going to be equal to d over 2 squared plus y squared to the 3/2. Okay. Now, if we make an assumption that we are a long ways away from the dipole, so in other words, if we're a long ways away from the dipole, then that means that y is going to be much greater than d. Okay, so we got the dipole and we're a long ways away. So if we make that approximation, so if we limit as d becomes, or rather as r, or rather y becomes much greater than d, okay, then what we've got here is now the limit of K sub E Q D divided by the term there, but then what happens is that would leave that just as y cubed, because the d term would be very, very small by comparison, so it would be negligible. So square root of y squared is y, and then cubed would be just y cubed. So that would indicate that the electric field goes as K sub E QD over y cubed. Okay, so that's off to the side. Now, your book does a similar sort of derivation, and the book does a derivation in which we have a negative charge, negative Q, we have a positive Q, some distance D away from each other, and it measures off in this direction right there and calls that distance Z because it turns it upwards. And the book comes up with an interesting sort of thing. They come up with E equals 2 K sub E QD over Z cubed. Well, that looks very, very similar to what we had before. Okay, so they both have the same property that the strength of the field drops off as the distance cubed. Okay, now that turns out to be exactly what happens, that it drops off as the distance cubed. Okay, and so that's an interesting sort of thing. In fact, it can be shown that the fields here, minus Q and Q, even if you're, I derived it off this way, the book derives it off that way, even if you derive it off that way, it's going to be equal to something over the R cubed. Okay, and so this is a property of dipoles. Okay, and in fact, the something in here has QD in it. Okay, now the prefix there, that turns out to be very, very complicated if you're not in a line here and a line there. To get off to the side, what you need are Bessel functions. Okay, nobody likes dealing with Bessel functions, so we're not going to do that for this class. That's more of a graduate level exercise right there. And so we're not going to worry about that. We're going to do it simple. I derived it off to the side. The book derives it off the ends. Either way works. Okay, now what you find is that you always get that the electric field is proportionate to, so it's always going to be proportionate to something that is equal to QD and divided by the R cubed. Okay, and so the dipole fields dropped off as R cubed. Now the QD turns out to come again and again and again in any equation related to dipoles, so we just give it a symbol, P. P is the dipole moment. We could say that for a dipole here in which we have minus Q, we have Q, okay, plus Q. If we are off in this direction here, and that's some distance Z, then as the book derives it, E equals 2 K sub E P over Z cubed. If, on the other hand, you go off this way, some X, then what we just derived will indicate this is equal to K sub E P over X cubed. Okay, and so in both cases, we got the P and we got the X cubed in there, it's dropping off. Okay, the other thing is the direction. Obviously it's going to be in this direction because you're closer to the positive. charge when you're that way. We already know from before, if you're off to the side, it's going to be in that direction. So we can define the dipole vector, dipole moment, as a vector. It's equal to q times the separation between the dipoles, and the direction of the vector is going to be equal to the direction between the negative and the positive. So from negative to positive defines the direction of the dipole moment. So this is the vector nature of it. So this kind of relationship is always going to be the case here with dipole fields. And remember, you get these dipole fields all the time, because all you gotta do is separate charge, and now you have an electric dipole.